In October 2019, a machine sitting inside a refrigerated chamber in Santa Barbara solved a mathematical problem in just 200 seconds. To find that same answer, the most powerful classical supercomputer on Earth at the time, a machine the size of 2 basketball courts, would have needed approximately 10,000 years of continuous processing. Comparing this machine to a standard computer misses the mechanics of the engine entirely. It operates on a separate set of physical laws that allows it to bypass the sequential limitations of classical processing. Every computation your phone or laptop performs is encoded in classical bits, existing as either a 0 or a 1. A quantum bit, or qubit, can be a 0, it can be a 1, or it can exist in a state called superposition, holding both possible values physically and measurably at the same time, until the moment it is observed. This property allows every single qubit added to a system to double the number of states the machine can hold at once. 10 qubits hold over 1,000 states. 20 hold over 1,000,000. The machine Google built in 2019, called Sycamore, contained 53 qubits, allowing it to hold approximately 9 quadrillion computational states simultaneously. Rather than checking possibilities one at a time, the machine explores every path through the problem at once. It turns computation from a sequential search into a simultaneous physical event. This exponential scaling eventually hits a hard physical limit. If we project this technology forward to a machine built with just 300 qubits, the numbers stop making sense in the context of our reality. The number of simultaneous states that a 300-qubit processor can hold is 2 raised to the power of 300, a number that stretches roughly 90 digits long. This 90-digit figure is larger than the total count of atoms in the entire observable universe. Even if you mapped every particle in every star and galaxy we have ever detected, a 300-qubit machine still commands more computational space than all of it combined. If every computational state requires a physical resource, like a particle, to represent it, our universe simply does not have the room to contain the work this machine performs. The arithmetic suggests that if the machine functions, and it does, it is drawing its resources from somewhere beyond the boundaries of our observable reality. In 1957, a Princeton student named Hugh Everett III proposed that when a quantum system is measured, reality branches. He argued that every possible result physically takes place in its own distinct version of the universe. The physics community dismissed the idea, and Everett left the field to work on nuclear targeting strategies for the Pentagon. In 1985, a physicist named David Deutsch realized that Everett's equations were more than a curiosity, they were an engineering requirement. He formalized the concept of a universal quantum computer that could, in principle, simulate any physical process. Deutsch's thesis was that a quantum computer works by reaching into these parallel versions of the universe. It uses the multiple instances of reality as a computational resource, performing the staggering amount of work across a vast number of branches simultaneously. Today, every quantum computer on Earth serves as a physical testament to Everett's mathematics. The many worlds theory is the leading framework for explaining why these machines work at all. They require other branches of reality because our own branch is too small to hold the calculation. If these parallel branches are physically real, we should see them, yet we experience a single definite world. This is due to a process called decoherence. A quantum system stays in superposition only as long as it remains perfectly isolated. The moment it interacts with a single air molecule or photon, information leaks out into the environment, and the branches of reality invisibly separate. This is why you never see a coffee cup in 2 places at once. Decoherence happens at everyday scales in a trillionth of a second. To stop reality from branching too early, companies like Google and IBM must keep their processors in absolute isolation. They use vacuum chambers and cryogenic systems to reach temperatures colder than deep space, building a wall that prevents the universe from looking at the qubits before the calculation is finished. Once the work is done, the machine must extract a single result. In 1982, Richard Feynman proposed that quantum machines could use the physics of interference to find the answer. Think of waves on water. A quantum computer is designed so that all paths leading to incorrect answers operate out of phase, causing them to cancel each other out. Simultaneously, the paths leading to the correct answer reinforce and amplify each other. The machine does not choose the right answer. It manipulates the physics of the computation so that the wrong answers subtract themselves from reality, leaving only the correct path to survive. This interference mechanism has immediate consequences for global security. Peter Shor's 1994 algorithm proved that a quantum computer could instantly dismantle the asymmetric math used to protect nearly all internet, banking, and military encryption. The response from the institutional level confirms the threat is real. In 2016, the National Institute of Standards and Technology launched an 8-year international competition to establish post-quantum cryptography standards, publishing the final requirements in August 2024. However, these new standards don't protect data that has already been intercepted. Under a strategy called Harvest Now, Decrypt Later, intelligence agencies are hoarding massive amounts of encrypted global communications. They are storing this unreadable data on servers today, waiting for the moment quantum hardware scales up to execute Shor's algorithm. The window for quantum disruption is open right now. Every piece of sensitive data captured and stored today is compromised the moment a large-scale processor can run the necessary calculations. Beyond cryptography, these machines suggest something about the nature of our existence. Toward the end of his career, physicist John Archibald Wheeler proposed that the physical world is not fundamental. He called his concept it from bit. Wheeler argued that every particle and field of force emerges from binary yes or no questions. In this view, information is the primary substance of the universe, and matter is simply a secondary effect of how that information is organized. This was supported in 2012 by experiments verifying Landauer's principle, which showed that erasing a bit of information releases a measurable amount of heat. Information has physical weight and a thermodynamic cost. It is as real as the chair you are sitting in. If Wheeler is correct, these machines are operating on the actual information from which our world emerges. We have built a tool that participates in the universe's own ongoing calculation, raising the question of whether our interventions change the final output, of the reality we experience.